Hello everyone, and welcome to today's tutorial on the basics of beamforming in RF and microwave antennas. By the end of this video, you'll have a clear understanding of what beamforming is, how it works in antenna arrays, the underlying signal processing principles, and its real-world applications in radar, 5G, Wi-Fi, and satellite communication systems. So, let's get started. Imagine a single antenna element. When it transmits a signal, it radiates energy in almost all directions, just like a light bulb spreading light everywhere. Now, if we increase the number of antenna elements to 4, the radiation pattern changes and becomes more directional. If we continue increasing the number of elements to 16, and then to 64, the main beam becomes even more focused. This is the essence of beamforming. By using multiple antennas and controlling their signals, we can concentrate the transmitted energy in a specific direction. The more elements we add to the array, the narrower and stronger the main beam becomes, allowing us to send or receive signals more efficiently. Beamforming is a signal processing and antenna control technique that allows us to steer the direction of maximum radiation or reception without physically moving the antenna. It's like replacing a light bulb with a flashlight. You still use the same energy, but now it's focused in one direction, giving stronger illumination where you need it. Beamforming works because multiple antennas, or antenna elements, transmit signals with carefully adjusted phases and amplitudes. The waves combine in space, adding up constructively in some directions, producing strong radiation and cancelling out in others, reducing unwanted energy. This constructive and destructive interference shapes and steers the radiation pattern, forming the beam. Consider a linear array of antennas spaced evenly at a distance, d. When all antennas transmit the same signal simultaneously, the strongest radiation occurs perpendicular to the array, called the broadside direction. If we introduce a small phase difference, known as a progressive phase shift, then we can change the main beam's direction. By slightly delaying or advancing each antenna's signal, we can electronically steer the beam toward any desired direction. For example, in this case, beam is steered by an angle of 30 degrees. And in the same way, by varying the phase of signals feeding to antenna elements, we can steer the beam on the other direction. Beamforming has widespread applications. In Wi-Fi, routers focus signals toward devices for stronger reception and higher speeds. In 5G, beamforming compensates for high-frequency losses by directing beams to users, improving coverage and capacity. In radar systems, electronic beam steering replaces rotating dishes, allowing fast, precise scanning of multiple targets. In satellite communications, beamforming creates narrow spot beams for specific regions, enhancing frequency reuse and efficiency. A real-world example is Starlink, which uses advanced phased array beamforming in both its satellites and user terminals to dynamically track satellites in low Earth orbit and deliver high-speed internet connectivity worldwide. There are 3 primary approaches to beamforming: analog, digital, and hybrid. Analog beamforming relies on RF hardware components such as phase shifters and variable gain amplifiers to control signal direction. It is relatively simple and power efficient, but typically supports only one beam at a time. Digital beamforming, on the other hand, processes signals after analog to digital conversion, enabling precise control, adaptive algorithms, and multiple simultaneous beams, though at the cost of higher computational complexity and power consumption. Hybrid beamforming combines the strengths of both methods, using analog processing for coarse beam steering and digital processing for fine control. This approach is widely used in 5G massive MIMO systems because it balances performance with hardware efficiency. Beamforming has evolved from analog radar systems in World War II to advanced digital implementations powering modern wireless technologies, from smartphones and Wi-Fi routers to satellites and radar networks. Using tools like Keysight, ADS, MATLAB, or CST, engineers can simulate beam patterns, adjust array spacing, phase shifts, and amplitudes, and visualize beamforming effects. Despite challenges like precise phase control, high-speed converters, and power consumption, beamforming remains a cornerstone of modern and future communication systems. In 6G, autonomous vehicles, satellite constellations, and IoT networks, beamforming will ensure efficient, adaptive, and focused wireless links, shaping the future of connectivity. I hope this tutorial helped you understand the basics of beamforming in RF and microwave antennas. If you found this video helpful, please give it a like, share it with your friends, and don't forget to subscribe to the channel for more tutorials like this.